Hello, this is Dr. Daystorms, and now we're going to be talking about combustion analysis and really start getting into some of the nitty-gritty about chemistry. Okay, and combustion analysis is a powerful tool or technique that you can use to help determine empirical and molecular formulas. But you do need to know a little bit more information before we go on. First off, your book has a much better picture of this, but just in general, the combustion analysis occurs where you put your sample in and you heat your sample up to the point where it breaks apart into the individual molecules. Then you use a carrier gas, and usually, many times we're talking about just O2, some oxygen. This will work for samples that are composed of either hydrocarbons, like alkanes, like ethane and methane and things like that. Or it'll also work with compounds that contain carbon, hydrogen, and oxygens. Things like carbohydrates. Okay, so what happens is, as the sample is compressed and breaks apart into its individual molecules, this allows for the elements to combine and what happens is all of the carbon is converted into carbon dioxide since it's a combustion reaction. And all that the copper oxide pellets are is to help make sure that all of the carbon is converted to carbon dioxide. Then what happens is the hydrogens are converted into water due to the combustion reaction. So you have some sort of material here that will absorb the water. Then anything that remains is carbon dioxide, and it gets absorbed by carbon dioxide, and then we just have any remaining oxygen in the form of O2 escape the apparatus. So if you know the mass of the water absorber before and you know it afterwards, you subtract it out, you can figure out how much hydrogen was produced. And then likewise, if you know the mass of the carbon dioxide absorber before and then afterwards, you can figure out how much carbon there was in the original sample. So let's just do an actual experiment here. We're going to calculate the empirical and molecular formula. I will tell you right now that this example here is perhaps one of the most complex. And there's an example that's a little more simple. It's in your textbook. And then again, I suggest that you do additional problems at the end of the chapter. Here, this is what's given. You're told that ascorbic acid, which is vitamin C, by the way, it contains only carbon, hydrogen, and oxygen. If a combustion analysis of 5.24 grams of ascorbic acid yields 7.86 grams of carbon dioxide and 2.14 grams of water, you need to calculate the empirical formula and molecular formula of ascorbic acid. You're given that the molar mass is about 176 grams. So this is our plan of attack. We have to determine the mass of carbon and hydrogen from combustion. The reason being is as follows. Any new carbon that's made, so any change in the mass of carbon dioxide, that can tell you the amount of carbon that there was. Likewise, any change in the mass of water tells you the amount of hydrogen that there was in the sample. So let's go back here. So we need to determine the mass of the carbon and the hydrogen from the combustion. We're going to subtract these masses from the initial amount of those absorbers to determine the original amount of oxygen. And likewise, we're going to now need to determine the molar ratios of carbon, hydrogen, and oxygen. The empirical formula has to be a whole number. It's got to be an integer of the molar ratios. And then finally, I'll show you how to determine the molecular formula once you know the empirical formula and the molar mass, which was given. You can't determine the molecular formula unless you know the molar mass of the original compound. Okay? So let's do an example, or let's work on this example. Alright, so we were given the fact that at the end, sorry about that. we were given at the end that there was 7.86 grams of carbon dioxide. Now, you would have to know how to figure out the molecular weight of the carbon dioxide, which was a different video. But if you do, it's going to come up to 44.01 grams carbon dioxide. Well, and that's equal to 1 mole of carbon dioxide. Well, based off of the molecular formula there, we know that 1 mole of carbon dioxide is equal to 1 mole of carbon, because there's 1 C in CO2. And we know from the periodic table that 1 mole of carbon is equal to 12.01 grams of carbon. Now let's check to make sure that everything cancels. So we have grams of carbon dioxide, grams of carbon dioxide, moles of carbon dioxide, moles, moles to moles of carbon. So the only thing left is grams of carbon. You multiply by everything on the top, you divide by everything on the bottom. If you do this, you're going to get 2.14 grams of carbon. Okay, so we're going to have to remember that. Now we're going to do the same thing for hydrogen, but using water. Okay, so we're given that the combustion analysis gave a result of 2.14 grams of water. We know that from the molecular weight that 18.02 grams of water is equal to 1 mole of water. Also, from the molecular formula, 1 mole of water has 2 moles, that's where some people make a mistake, of hydrogen, because it's H2O. And from the periodic table, we know that 1 mole of hydrogen is equal to 1.01 grams of hydrogen. Now let's just check to make sure that everything's going to cancel. We have grams of water, and that would be grams of water. A mole of water on top, moles of water on the bottom, moles of hydrogen, so the only thing left is grams of hydrogen. Okay, so let's figure out how many grams. You multiply everything on the top, you divide by everything on the bottom, and you're going to get an answer of 0.24 grams of hydrogen in the original sample. So, remember, if we go back to the beginning, there is 7.86 grams of vitamin C, of ascorbic acid. Of that original 7.86 grams, 2.14 grams was carbon. And we need to subtract out 0.24 grams, which is hydrogen. So 7.86 minus 2.14 minus 0.24 is equal to 2.86 grams of oxygen. So we know the original sample contains, I'm just going to rewrite this, 2.14 grams. Oh, whoops, I made a mistake here. I'm so sorry. It's not 7.86. My math was correct. I just wrote down the wrong one. It was 5.24. Okay, 5.24 grams of vitamin C. So originally it was 2.14 grams of carbon in the original sample, 0.24 grams of hydrogen, and 2.86 grams of oxygen. So that's why if you add all those up, it comes to 5.24 grams. Now we can't use grams directly to determine the empirical formula. And that's because a mole of carbon weighs more than a mole of hydrogen, and a mole of oxygen weighs more than the other two. In fact, it weighs more than a mole of the other two combined. So we need to convert each of these moles into grams. So I'm going to have to go to another page. So we have 2.14 grams of carbon in the original material. Let's convert that to moles. We know from the the molecular weight, or the atomic mass of carbon from the periodic table is 12.01 grams of carbon is equal to 1 mole of carbon. If you do this, you get within error 0.178 moles of carbon. We're going to do the same thing with the hydrogen. The original sample had 0.24 grams. 0.24 grams of hydrogen. We need to convert that to moles. Right? So we have now 1.01 grams of hydrogen is equal to 1 mole of hydrogen. If we do that, we get the answer of 0.24 moles of hydrogen. Finally, we have to figure out the oxygen. We have 2.86 grams of oxygen. We know that 16.00 grams of oxygen is equal to 1 mole of oxygen. That comes out to 0.179 moles of oxygen. We almost have the empirical formula now, because if you notice, 0.178, 0.179 are about the same. 0.24 is larger, and we need these to be whole numbers. So what you do is you divide all of these by the lowest number, which would be 0.178. If you divide 0.178 by 0.178, you're going to get 1. Okay, so let me erase a little bit, so that way I can do it on the same sheet. Okay. Alright, so when we divide 0.178 by 0.178, we're going to get 1 mole. I'm sorry about that. We're going to get 1. Likewise, if we divide 0.179 by 0.178, we're going to get 1. So that means the ratio of C and O are the same. However, this is where this problem becomes more tricky. If you divide 0.24 by 0.178, you actually get 1.33. That's not a whole number. So the question becomes, and this is the number of carbons, the number of oxygens, and the number of hydrogens. If you need to, oops. If you need to, you can actually write this as a ratio, and you would see that it's not 1 to 1 to 1 or 1 to 2 to 1. The problem here really has to do with this 1.33. So how can we make 1.33 essentially a whole number? Well, 0.33 is approximately 1/3. So we need to multiply everything by 3. So if we multiply this by 3, we're going to get 3 carbons. If we multiply this by 3, we're going to get 3 oxygens. If we multiply this by 3, you're going to get 4 hydrogens. So that means that the empirical formula is C3H4O3. That's the empirical formula. That right there is the answer to the first part. C3H4O3. Okay, so let's go back to the problem that we were talking about. We determined the mass of the carbon and hydrogen. We've subtracted to get the oxygen. We determined the molar ratios, and now we have the empirical formula in whole numbers. Okay? So, now let's continue on to find the molecular mass. the molecular formula. We are given that the molecular mass is 176 grams. And that 176 is very, very important. Okay. So we know that the molar mass is 176. So that's the same thing as saying 176 grams per mole. That's literally what that means. And we know that the empirical formula is C3H4O3. So now let's figure up how much does a mole of that empirical formula weigh. Okay? So we have to take 3 times 12.01 grams, 4 times 1.01, because that's how many hydrogens there are, and 3 times 16.00, 16.00, since it's how much oxygen there is. Okay? So, when you add all of those up, you get 88.07 grams per mole. So if you notice, the empirical formula would weigh 88.07 grams per mole, but the molar mass of vitamin C is 176. So if we take 176 and we divide that by 88.07, we get 2. So that means that the molecular formula, okay, is going to be 2 times the empirical formula. So that means instead of having, it'd be 3 times 2, which is C, would be C6. The H's would be 4 times 2, which is H8. And the oxygens would be 3 times 2, which is C6. So this right here is the molecular formula for vitamin C, or ascorbic acid. As I mentioned, this is probably the most difficult problem that there could be for this type of problem. Please go through and try to work additional problems and see additional examples both inside the text, inside the chapter of the text, and at the end of the chapter. Because practice will make perfect of this. If you have any problems or any questions, please come visit me during office hours and set up a time and we can work it out. Thank you, and I'll see you in class.